Okay, so this week in our parent class, we're starting a new chapter, and the unit we're covering is on symbolic logic. And for this chapter in particular, there's not a whole lot of prerequisite content that we could really cover that's going to directly help with the material we cover. So rather than focus on prerequisites, what I'm going to do in this section is, or in this chapter for the most part, is just get extra practice in our support course on the same kind of stuff that we're going to be doing in the parent class. So again, this unit or this section that we're working on this week is not prerequisite material. It's just reiterating things that we've already covered and getting you extra practice on the exact material that we're looking at in the parent course. So because we talk about a lot of the terminology that we use in this lecture today, in the parent class, I'm not going to go through and define everything again, but I might do little reminders of what certain terms mean. So first thing we're doing is looking at compound statements and what I'm going to call simple statements. And I don't remember if your book uses the term simple statements, but basically we're going to say a statement is simple if it's not a compound statement. Okay? So specifically what we're doing, we first want to identify whether a statement is simple or compound. And then if it is compound, we want to do a little bit more. We want to identify what the component statements are by giving them labels, P and Q. And then we want to identify what the connective is that's being used in that statement. So from the parent course, you will remember that connectives are things that join simple statements. And when we do that, we call them component statements. Connectives as words are things like the words and or. And then we also think of negations, not, for example, as a connective as well. So starting with this first statement, the stove is on. I don't see and or anything like that showing up in this statement. The statement only has, there's really just one single thing being communicated in this statement. This is a simple statement. It's not compound. There's not two statements that are being combined somehow. So that's all there is to do for that one. Number two says the sun is shining or the moon is out. So this one is a compound statement because the word or is the logical connective that's being used, and it's joining these two component statements. The sun is shining, the moon is out. Each of these is a component statement coming together to make this compound statement. So the instructions wanted me to identify the component statements with P and Q. Let me first say that this is compound. Okay, it's a compound statement. P, I'm going to call the sun is shining. The sun is shining. That's our first component statement. Q is going to be the component statement. The moon is out. Okay. And then in the instructions it said that if it's compound, we wanted to identify the component statements using those labels, P and Q. And then we also wanted to identify which connective is being used. And in this case, the connective is the word or, which, remember, in the language of symbolic logic, we call that a disjunction. Okay, so the kind of connective that we're using is a disjunction, and it shows up as the word or in this compound statement. Okay, so on the assignment for our support course this week, you're going to be doing some of this. You're going to be identifying whether statements are simple or compound, and if they are compound, you're going to be doing this extra work here. Okay. Moving on, we want to now look at truth values. So remember, the point of studying statements in symbolic logic is to determine whether statements are true or false using the techniques of symbolic logic. And for these ones, I'm using mathematical statements. These show up a lot in this section. And the reason I'm using them is because it's straightforward to determine whether these component statements that are showing up in each one of these compound statements are true or false. Mathematically, they have to be one or the other. So starting with this first example, 4 plus 3 equals 7, and 19 is less than 12. So the first thing I want to do is recognize that this is a compound statement with two component statements, and the logical connective is a conjunction. It's the word and. Remember, from the parent class, in order for a compound statement using a conjunction to be true, both of the component statements need to be simultaneously true. 4 plus 3 equals 7 is true. This is a true statement. However, 19 is less than 12 is a false statement because 19 is not less than 12. And the fact that one of these statements ended up being false means the entire compound statement must also be false. Okay? And that really boils down to which connective was used here, the word and. Number 2. Number 2 says 21 divided by 7 equals 3. This is true. Okay? Or 2 cubed equals 6. 2 cubed does not equal 6. 2 cubed equals 8. So this one is false. Just like the previous problem of the previous compound statement, we had a true compound statement and a false compound statement. However, in this example, we're using a different logical connective. We're using the word or, which makes this a disjunction. This becomes true, and the reason for that is if you have a disjunction, so if you're using the word or, then you only need at least one of your compound or your component statements to be true in order for the entire compound statement to be true. So because one of the statements ended up being true, it didn't matter what the other one was. This ended up being false. It could have also been true, but in either of those cases, we would have had true for our compound statement. The only way this could have been false is if both statements were false, both component statements. Okay, one more example. This one says 3 times, and then in parentheses, 1 minus 4 equals -9, and 5 squared equals 25. So is this one true? Well, in the parentheses, 1 minus 4 is -3, and 3 times -3 is -9. So this does come out true. Okay? 5 squared is also known easily to be 25, so that's also true. Because we're dealing with a conjunction, and the word and is showing up here, both statements need to be true in order for the entire compound statement to be true, which is what's happening in this case. So we would say that this one is true. Okay? All right. These are very straightforward, and it really just boils down to knowing what are the conditions for these different logical connectives to be true or false. Let's move down here. It says, let P be the statement, the cow's name is Ted, which is an interesting name for a cow, and let Q be the statement, I have no bacon, which is a tragedy. Write the following symbolic statements in words. So this one, this is the first example that we're coming across where we're now using the symbolic representation of these statements. So remember, when you have this symbol here that looks like a capital V, this is a symbol representing a disjunction, which means we use the word or here. So if I wanted to read this just in its symbolic, using the terms for the symbols being used here, this would say P or not Q. That tilde right there is for a negation, like we talked about in the parent class. So P, the statement P is, the cow's name is Ted. I'm going to write that. Oop, I should capitalize Ted. The disjunction here tells me that I need to use the word or next. The cow's name is Ted or not Q. So this means the negation of Q. If Q is the statement, I have no bacon, what would the negation of that statement be? Well, the negation of having no bacon is having bacon or having some bacon. You know, there's some variants that are that you could use there. So I'm just going to say, or I have bacon. Bacon, yeah, there we go. So the statement itself is kind of ridiculous, but that's not really the point. You know, this doesn't need to be a statement that makes much sense in, you know, how you would use it in a kind of everyday language. The point is understanding how the symbolic representation of these statements connects to the statements in words. Okay. Next one is similar. It says not P and Q. This like upside down capital V is for conjunctions. It's the symbol for the word and, basically. So we start with not P. P says the cow's name is Ted. So we need the negation of that, which would be the cow's name is not Ted. That would be the negation of that statement. As a conjunction, we want to use the word and. Then we follow that with the statement Q, which is I have no bacon. Okay? I mean, and that's yeah, it's fairly straightforward. All right. One last thing I want to touch on. There's a lot covered in the parent class, and I don't see much point in just going through all of it all over again, but I just kind of want to reiterate some of the important parts. So what I want to do now is talk a little bit about truth tables, because we spent a lot of time in chapter 3 dealing with these truth tables. So this is saying we want to create excuse me, we want to create a truth table for each of the following statements. And then there's going to be a follow-up question at the end. So these are both compound statements. And you remember, for truth tables, what we want to do is start by creating a column in our table for each component statement that appears. Okay. Now, Q is actually not a component statement in this compound statement, but not Q is, or the negation of Q is. So I want to include that in its own column. Okay. Now that I have the P showing up here, the not Q showing up here, I want to make a final column where these get joined together by that disjunction. So this is going to look like P or not Q. Okay? Now remember, because P and Q are the only letters appearing here that represent component statements or simple statements, we start by finding all possible combinations of truth values of these. So they could both be true. P could be true and Q could be false. We could reverse that, and Q could be false while P could be false while Q is true, or they could both be false. Those are the only 4 possible combinations of truth values for those two statements. Moving to the next column, not Q will be true anytime Q is false, and it will be false anytime Q is true. It will always have the opposite truth value of Q. So if this is true, then not Q is going to be false. If that's false, this will be true. If that's true, that'll be false, and that false implies that this is true. Excuse me. Okay. Finally, in this column here, we're dealing with a disjunction, and the component statements are P and not Q, which are represented by the first and third columns in this truth table. Disjunctions are always true so long as at least one of its component statements are true. The only time it's ever false is if both statements are simultaneously false. So comparing column 1 to column 3, I have one true statement appearing here, which means the entire the compound statement or the disjunction will be true. Once again, I have another true statement appearing here, which means the disjunction will be true. In this third row here, both P and Q appear to be, or P and not Q, they appear to be false, which means the disjunction is false. And then finally, in this last row, not Q is true, which means the entire compound statement is true. Excuse me. Okay. So this completes the truth table. And again, the point of a truth table is to determine all possible truth values of this compound statement, determined by all possible combinations of truth values for the simple statements P and Q. All right, this next one looks a tad more complicated, but it's not that bad. Same idea. We want to start by creating a column for P and a column for Q, like this. And then you kind of want to work from the inside of the parentheses out, starting with negations wherever they appear. So I have a not P showing up here. That's going to get its own column. I've already dealt with the Q in the second column, so not P and Q, the things in parentheses there, are being joined by a conjunction. So I'm going to create a column for that conjunction, not P, and, oops, I almost made that like a letter A, not P and Q. And then finally, we take the negation of that entire thing, which is going to be its own column right here. Not P. I did it again. I really want to write a capital A there, but it's not a capital A. It just kind of looks like one. Same thing as before. I want to start by finding all possible combinations of truth values for P and Q. And for the follow-up question that we're going to do after this, it's really important that I choose them in the same order that I chose them here. So true, 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 false, false, true, false, false. Okay? True, 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 false, false, true, false, false. Okay? Not P. Looking at the negation, I'm going to compare that to my first column. So I have true, true, false, false, which means this will be false, false, true, true. The opposite truth value that of each individual truth value that's showing up in this column. Over here, I have not P and Q. So not P appears here, Q appears here. I'm comparing columns 2 and 3 for this guy. And because this statement is a conjunction, I now need both of these to be true in order for that to be true. In this first row, one of my statements is false, so that makes the whole thing false. In this statement, in this row, both of my statements are false, so the conjunction is false. In my third row, both statements are true, so that means this would come out true. And then finally, one of my statements is false in my fourth row, making the entire compound statement false. Finally, I want the conjunction, or not, sorry, not conjunction, the negation of this previous column as my final column. So whatever truth values are appearing in each of these rows, I want the opposite truth value showing up here. Okay? All right. As a final question, we're asked whether the statements from the previous two problems are equivalent. So is the statement P or not Q equivalent to not, and then in parentheses, not P and Q? And the truth tables reveal whether they're equivalent or not. The way we determine if they're equivalent is if every combination of truth values in this statement yields the same truth value for the compound statement as it does here. And that comes down to looking at these two final columns in each of these truth tables and seeing if they came out the same. So notice I have true, true, false, true here, true, true, false, true here. These two columns completely agree with each other, which means these two statements are equivalent. Now, I mentioned before, it was really important that we put these combinations of truth values in the same order here as we do here for the first two columns in each table. And the reason for that is if I mixed up the order here, then that's going to cause the order of all these other columns to be mixed up as well. And even in that case, these last columns may appear different when they are in fact the same. So really, really important that the first two columns here have the same order when you're writing your truth values as they do here. But these two statements are equivalent. I'm just going to write yes with an exclamation point. Why not? Okay, yes, they are equivalent. That's going to wrap it up for this lecture.